Have you ever felt as though time is accelerating in recent years? There might actually be a reason for that sensation. Something unusual is occurring with our planet. So, we understand that the Earth rotates on its axis. At least most of us accept this fact. Unless, of course, you belong to the Flat Earth Society, in which case, greetings. But operating under the assumption that the Earth is indeed spinning, we recognize that it completes one full rotation every 24 hours, correct? Actually, not quite. The Earth's rotation isn't constant. It can accelerate and decelerate during different periods, and the present moment happens to be one of those periods. The Earth is spinning more rapidly than it ever has before. More precisely, this represents the fastest rotation since we began officially tracking the Earth's spin, which only extends back to approximately 1970. So in reality, it's the fastest the Earth has rotated in at least 55 years. And the velocity of the Earth's rotation has actually been increasing since approximately 2020. If the flat earthers are still with us, I'm certain there's some conspiracy theory about how that timing aligns with world events. And then the shortest day on record occurred in July 2024, with the Earth completing a full rotation 1.66 milliseconds faster than 24 hours. The average human eye blink lasts between 100 and 150 milliseconds. So we're talking about 1/100th of a blink. Regardless, let's address the pressing question. Should we be alarmed? Well, consider this perspective. If you expand your view far beyond the 20th century and travel backward through time, the Earth is actually rotating much more slowly than it is today. 600 million years ago, a single day lasted only 21 hours. It's genuinely confusing, so here's what's happening. There are numerous factors that influence the rotation of the Earth. The Sun and the Moon are major contributors, but the Earth's own composition can also alter how rapidly it spins on any particular day. The Sun possesses enormous mass, but it actually exerts a fairly minimal influence on the Earth's rotation. If anything, solar energy actually encourages the Earth to spin faster, but this effect is vastly overshadowed by our closest celestial neighbor, the Moon. That body actually exerts a very powerful influence on our rotational speed. Most of this occurs through a phenomenon called tidal friction. This is a highly simplified explanation of how it functions. So, the Moon's gravitational force pulls on the water in Earth's oceans and creates a bulge. This represents high tide. And as the Moon orbits the Earth, it drags that bulge along with it. Except the Earth itself is actually rotating faster than the Moon's orbital period, so the bulge is trailing behind the Earth's rotational speed, and that will actually function to decelerate the Earth. It adds approximately 2 milliseconds to the length of each day every 100 years. And over a sufficiently extended time frame, it will ultimately slow the planet's rotation until it synchronizes with the Moon's orbit. But literally every living thing on Earth will have perished by the time that occurs. So don't spend too much energy worrying about it. So on average, the Moon causes the Earth to spin more slowly. But currently, the Moon is also among the factors causing the Earth to spin faster. The Moon doesn't invariably orbit around the Earth's equator. Sometimes it shifts to orbit nearer to the poles. And the present time happens to be one of those periods. We refer to this as declination. The closer the Moon approaches the Earth's pole, the higher the declination value. And during these intervals, the Moon exerts less gravitational pull on the Earth's equator and more on the polar region, which actually causes us to rotate faster. But this lunar cycle is entirely normal. So it isn't the sole factor that would account for the Earth rotating faster than it has in decades. And for the final component of this puzzle, we need to examine the Earth itself. The distribution of mass across the planet is going to significantly affect how rapidly we spin. Consider a figure skater spinning on ice. When their arms are extended outward, they rotate slowly. When they draw their arms inward, they accelerate. Earthquakes can trigger the Earth to spin faster. Typically, what occurs is one tectonic plate sliding beneath another one. That forces more rock downward beneath the surface of the Earth. More mass shifting toward the center equals faster rotation. We're discussing very minute amounts, however. The Japanese earthquake in 2011 accelerated the Earth's rotation by 1.8 microseconds. That's 1/100th of a millisecond, which was 1/100th of a blink. So, an extremely small amount. But these effects accumulate. Water also influences the distribution of mass around the globe. Yes, we can attribute this to climate change, but this happens through a genuinely peculiar mechanism. So polar ice caps are melting. That introduces more water into the ocean, despite what Mel Gibson might attempt to tell you, because the ice currently sits on land. And when it melts, it can then flow into the water. But in this scenario, when we have more water migrating from the poles toward the equator, It's like a figure skater extending their arms outward. It's supposed to slow them down. But there's an even more substantial effect caused by the mass of the ice in the polar regions. You see, these ice caps represent enormous concentrations of mass, and the Earth's gravitational force pulls them inward toward the center. And that force is actually sufficient to compress the Earth slightly and cause the entire planet to bulge outward at the middle. That's considerably heavier than just the ocean water alone. But as the ice caps melt and the weight becomes more evenly distributed, the Earth is becoming less compressed. It assumes a more circular shape. The figure skater's arms come inward and we spin faster. So, what does all of this actually mean? Well, since the Earth has generally been rotating more slowly over time, we've been adding leap seconds to the standard day in order to maintain synchronization with the Earth's rotation. This has occurred multiple times now. The most recent leap second took place in 2016. So, when we state that one day equals 24 hours, we're actually rounding downward slightly. It's truly 24 hours plus a few seconds. But if the Earth continues to accelerate its rotation, then we might ultimately need to subtract one of those leap seconds, essentially reducing the length of a day back down closer to where it stood when we began measuring the Earth with atomic clocks back in the 1970s. Now, unless you're the individual responsible for the GPS network or some other critical timekeeping system, I wouldn't lose sleep over it. There is definitely far more concerning phenomena occurring on the Earth, but this particular one is somewhat fascinating to understand. Now here's something genuinely remarkable. This is footage captured inside the Sun's atmosphere. It was just released by NASA, and the images were recorded by a spacecraft designated the Parker Solar Probe. What we're observing here is the Sun ejecting electrically charged particles into space. The large cloud-like formation is a fragment of the corona. That's essentially the outer layer of the Sun, and everything that you see streaming past the camera represents the solar wind. It's a continuous flow of electrically charged particles that surge across the solar system, essentially generating solar weather. The Earth is largely shielded from this material by a magnetic field. But occasionally, a substantial piece of this corona gets expelled into space by the Sun's own energy, what we call a coronal mass ejection. And sometimes those will strike the Earth, producing auroras in the northern sky. And if the ejection is sufficiently powerful, it can also disrupt our electrical grids and communication systems. So, we've understood for quite some time that this happens, but right now marks the first time that we've witnessed it at close range. The Parker Solar Probe was launched in 2018, and it carried the mission of approaching closer to the Sun than any human-made object. It would essentially become the first artificial object to touch the Sun. That achievement occurred when the spacecraft completed its first close approach to the Sun in 2021, when it penetrated the corona for the first time. Then the probe would travel outward to Venus, where it would utilize the planet's gravitational force to slingshot itself back toward the Sun, drawing closer and closer to the star with each successive pass. Currently, the Parker Solar Probe is positioned just over 6 million kilometers from what we define as the surface of the Sun, which lies far below the corona. This represents the closest the probe will approach. It doesn't possess sufficient fuel to continue flying around Venus and accelerating, but it's already traveling fast enough that it won't be drawn into the Sun or anything of that nature. So it's going to continue making these close passes through the atmosphere and gather as much data throughout the process as possible. There are several important things that we're attempting to discover with this probe. One genuinely peculiar fact about the Sun that we don't comprehend is that the surface of the star is actually considerably cooler than the outer corona layer. So, it measures approximately 5,500 degrees Celsius on the surface of the Sun. But when you reach out to the corona, it heats up to millions of degrees. Sounds rather counterintuitive, doesn't it? You would assume that if the Sun serves as the source of all heat in the solar system, then it would originate from the center, but it doesn't. The heat is actually located on the exterior. There's also the enigma of the solar wind. We know that it exists, but we don't understand how it exists. We don't comprehend the forces that generate the wind or what propels it outward into space. So, we are attempting to trace the origins and the movement of those electrically charged particles. And even if we can't fully understand the solar wind, we do want to improve our ability to predict it. Right now, we don't know if a coronal mass ejection is approaching until it's already in transit. So, that doesn't provide us with much time to prepare. Most of these simply produce some beautiful lights in the sky and perhaps a momentary flicker on the power grid. But eventually, a massive solar storm will arrive. And when it does, we are going to discover what life is like without electricity, without internet, without communication of any kind, and things won't proceed well. So to conclude that discussion, don't worry about the Earth's rotation. It's perfectly fine. Do worry about the sun because it might destroy us all. There's probably nothing we can do to prevent it, but we might be able to at least detect it approaching, which might actually be worse.